Hi everyone, my name is Miguel. I am the team leader of the team number 3. Today we are viewing about thermal stress and phase changes. My teammates' names are Dana Sofia Rivera Rivas, me, the team leader, Miguel Ángel y Andy Sánchez, Eric Alejandro Treviño Almaguer, Mauricio Arnoldo Vázquez Zavala, Ángel Gabriel Chávez Parra. Next we are seeing the index. Okay, this is our index. Numbers, besides the the titles, are subjects, are not pages. Okay. First, we have introduction to heat. Then we have three forms of heat transfer: radiation, conduction, convection. What is thermal stress? Formula of thermal stress: everyday examples and everyday examples too. Bridges, expansion joints, thermal shocks in glass. What is a phase change? Types of phase changes: heating core, latent heat, example boiling water, example melting ice, phase diagram, relationship between thermal stress and phase change, extreme examples, pipes freezing, conclusion and questions. Okay, first we have, like I said, introduction to heat. As you can see in our right, I guess heat doesn't mean the same as temperature, and we are knowing why. Heat is a form of energy that is transferred between bodies due to a difference in temperature. It always flows from the object with higher temperature to the one with lower temperature until both reach thermal equilibrium. This process of energy transfer is fundamental to understanding numerous phenomena in daily life, from how a pot is heated on the stove to how an engine works. Why materials expand or how the human body maintains its temperature. Heat shouldn't be confused by temperature. Temperature measures how hot or cold a body is. Heat is the energy that moves from one body to another due to the temperature difference. Additionally, heat can be transferred in three main ways: conduction, convection, and radiation, which explain how it spreads in solids, liquids, gases, and even in vacuum. Right. Well, then we have three forms of heat transfer: radiation, conduction, and convection. First of all, conduction. This is the transfer of heat between 2 points of a body that are at different temperatures without any transfer of matter between them. The best conductors of heat are metals, while air is a poor conductor. Objects that are poor conductors, such as air or plastic, are called insulators. Radiation is the heat emitted by a body due to its temperature. In this case, there is no contact between the bodies, nor are there any intermediate fluids to transport the heat, simply by virtue of the existence of the body, a solid or liquid, at a higher temperature than body B. There will be a transfer of heat by radiation from A to B. Convection is a mechanism of heat transfer by a mass movement of circulation within a substance. It can be natural, proceeded, produced solely by difference in the densities of matter, or force, when matter is compelled to move from one place to another. For example, air with a fan or water with a pump. It only occurs in liquids and gases where the atoms and molecules are free to move within the medium. What is thermal stress? It's a mechanical stress is caused by a temperature change that prevents a material from expanding or contracting freely. This can happen when temperature changes uniformly or not uniformly, leading to physical damage like cracking, warping, or buckling. If the material strength is exceeded, factors that compose it: air temperature, relative humidity, wind speed, solar radiation, or heat sources. The thermal stress formula is mm, sigma represents the thermal stress. E is the Young's modulus of the material. Alpha is the linear coefficient of thermal expansion. Delta T, or the temperature difference, is the change in temperature. Okay, now we can watch the definition of thermal expansion. Thermal expansion explains how bodies increase their dimension when the temperature rises and decrease when it falls. Linear expansion, length, used for bars, rods, wires, tubes, thin plates, diameters, ready, etc. Delta L, variation in length or change in length. Alpha, linear thermal expansion coefficient of the material. It is a specific property of each material that indicates how much it expands per degree or temperature. L, initial length of the object. Delta T, variation in temperature, which is calculated by subtracting the initial temperature from the final temperature. T final minus T initial. Okay, the new length is, the first L is final length of the object. L0 or LL, initial length of the object. Delta L, change in length, that is the variation in length. Next, surface expansion area, used for sheets, plates, metal surfaces. Delta A is the change in area. Beta is the superficial or aerial thermal expansion coefficient. A0 is the initial area. Delta T is the change in temperature. Volumetric expansion, volume, used for 3D solids, liquids, gases within containers, etc. Delta B is the change in volume. Y is the layer of gamma, and that means the volumetric thermal expansion coefficient. B0 is the initial volume. Delta T, as I said before, is the change in temperature. Now, expansion of openings. It means that holes in place expand, just like the material. It means delta T, change in diameter. Alpha is the linear thermal expansion coefficient. D0 is the initial diameter, and delta T is the change in temperature, as I always have said before. Now, it's expansion with thermal stress, and is when it's not allowed to expand. If the body is fixed and cannot expand, as I said like 5 minutes ago, sigma, E, or modulus of Young, alpha, and delta T. Okay, now I'm going to say some everyday examples. First, we have linear expansion, lengths, diameters, radii. Railroad tracks. On hot days, the rail expands, and that's why spaces are left between them. If not, they would bend. Electrical cables. Cables are tighter in cold and looser in heat because they expand. Metal jar lids. To open a lid, we put hot water on it. The diameter of the lid expands and it loosens. Surface expansion area. Metal plates that cure when one face is heated more, for example, in the sun. That face expands more and the plate bends. Pavement with cracks. Asphalt expands with heat and contracts with cold, which is why it expands in joints. We can see an example in our left with a tiny little box before heating and after heating. Okay, well, now my partner is next.
Bright expansion joints. Expansion joints are separation of special spaces that are left in the structure of brights to allow them to expand and contract due to temperature change. All material expands when it's hot and contracts when it's cold. If a bright were a single bright piece without this space, when dilating it could crack. The form or inactive due to enormous internal forces. Main function. The main function of expansion joints in a bridge is thermal accommodation. Bridges are material of concrete and steel get strengthened by heat and shrink upon cooling. Thermal movement without expansion joints would create huge internal stresses, causing cracking, spalling, and even structural failure. A normal bridge can or shrink by several inches during seasonal temperature fluctuations, and that makes expansion joints necessary to handle stress. Furthermore, expansion joints also deal with movement induced by traffic loading. When large vehicles travel over a bridge, the bridge bends and deflection results. Suspension joints enable these dynamic movements without introducing pressure, stress, contraction, or at strategic connection point. This aspect is especially critical for long-span, heavily trafficked commercial bridges. Why are suspension joints necessary? Thermal suspension perspective. All construction materials such as steel, concrete, and asphalt have a specific coefficient of linear thermal expansion. This coefficient determines how much a material will lengthen or shorten per degree of temperature. If a base experiences a temperature increase, each segment tries to find by delta L equal L delta and delta T and alpha, because price can be tens or hundreds of meters long. Even small values of a lead to significant dimensional change. With expansion joints, such change would generate compressive stresses in hot weather, pushing inward, tensive stresses in cold weather, pulling outward. Both types of stresses can accumulate and material mechanical strain causing bending or building cracks in the deck, damage to support beams, structural instability, collapse in extreme cases. How they work depending on the material. Steel breaks. Thermal behavior. Steel has a high coefficient of thermal expansion, approximately 12 can um, this means steel brakes expand and contract significantly with temperature change. How expansion joints work? Expansion joints must allow large longitudinal movement. Still, brakes often use sliding plate joints or finger joints, which can open and close easily. Bearing support devices under the bridge also allow horizontal movement to prevent stress buildup. Why necessary? Steel reacts quickly to temperature change. Without joints, the structure would buckle or bend. How they work depending on the material. Concrete bridge. Thermal behavior. Concrete has a lower thermal expansion coefficient, but still expands noticeably because bridges are long. Concrete also creates slow deformation under load, adding to movement over time. How expansion joints work. Joints continue for moderate thermal movement, plus long-term wrinkles and quick. Double sealed or elastomeric joints are common, allowing controlled movement while keeping out water. Concrete slabs may have side-cut compression joints to avoid random cracking. While necessary, concrete can crack easily due to internal tensive stresses. Suspension joints reduce those stresses. Thermal shock in glass. Thermal shock is a phenomenon that occurs when glass undergoes a sudden change in temperature, either heating up or cooling down suddenly. This rapid change causes some areas of the glass to expand while others contract, generating internal tension that can cause the glass to crack or even fracture suddenly. Why does it happen? Glass, like most materials, expands with heat and contracts with cold. The problem appears when one part of the glass heats up quickly; it expands, while another part remains cold; it doesn't expand equally. This creates a stress imbalance within the material. If the stress exceeds its internal resistance, the glass breaks. What is a phase change? A phase change is the process by which a substance passes from one physical state to another, solid, liquid, or gas, due to a heat exchange, without its temperature changing during the process. What causes them? Phase change occurs when a substance absorbs or releases heat. Absorbs heat with fusion elimination. Releases heat, solidification, condensation, and deposition. This heat is called latent heat and is used to break or form bonds between particles, but while temperature doesn't change why the phase change occurs.
Now, we are going to talk about the heating curve. The heating curve is a graph of temperature in relation to the amount of heat added. The heating curve shows the temperature change that causes the substance to absorb an increased amount of heat. We can also observe that the temperature remains constant while the change of state is in progress. The temperature stabilizes because all the heat energy is used to break the intermolecular forces. Normally, it's graphed with x-axis, that is the amount of heat added, and the y-axis, that is the amount of temperature. As heat is added, the substance goes through stages where temperature increases. There are the inclined lines. Here, heat causes particles to move faster. Temperature rises. An example of that is a solid heating up before melting, a liquid heating up before boiling. First, a phase change occurs. There are the horizontal lines in the graph. During fusion or vaporization, heat is absorbed, but temperature does not change. That incoming heat is used to break bonds between particles, not to increase temperature. It's called latent heat. The latent heat refers to the energy required by a substance to change. This change involves going from solid to liquid phase, we speak of latent heat of fusion. And when the change occurs from liquid to gaseous state, we speak of latent heat of vaporization, where Q equals M plus L. An example of that is if heat is applied to a piece of ice and it begins to rise in temperature upon reaching 0 degrees Celsius, the changes from solid to liquid state will occur. This temperature will not vary, even if heat continues to be applied, until the ice has completely melted. Once melted, the water will begin to rise in temperature, again until reaching 100 degrees Celsius, where the phase changes to vaporization occurs, maintaining a stable temperature until the water completely evaporates.
Relationship between terminal states in the place changes. Who are you related? I insist The energy the phase changes to general lateral stress when the material changes place if the volume increment decrease abruptly. That change is the volume in produce expansion of current, which in general internal tensions in examples. Water expansion when it decreases negative 9%. If to inside a closed pipe of the counter, this expansion generates enormous straits and that can break the material. Metals contract strong when to substitute. This casting, this correction create internal straits that the process cracks. The enzymes and terminal the thermal straits indicate local phase changes if material receives intense bed the 1 point head of phasers reaches the metering or boring point before the resists change bases everything that inspection of countries generates the terminal straits that confracture the terminal. And the example, heating glass with the raw touch at the 1 point can't melt of the softened that the area, while the rest stays cold. Key generate tensions then make our process. See and since both the phenomenon depend of the head transformer, but terminal straits and in the phase change occur because the material absorbs and loses head has limited terminal conductivity and responding with volume with change of the state transition. General conclusion. Conclusions. The head terminal straits in the phase change of fundamental concept and explain how material and systems respond to temperature variance in the boundary in the and generate in voids and environments. Excuse me. Um, through of the study of the head transformer terminal expansions in the mechanisms of the phase transitions. When the standard, the temperature does not simply affect bone and affect a whole hot or cold in object fields. It determines how material behaves in the structural and molecular level. It determines the then terminal expansion reveals how the materials change dimensions with the temperature, often producing terminal internal straits that um, can deform of fractured structures when expansion is destructive, destructive. Everyday examples so much row rows, strokes, bright expansion joints in the terminal show in the glass industry the practical importance of managing the effects in real world applications. Um, Phase change further demonstrate that matter absorbs of raised energy without changes temperature while transforming with one solid liquid in the gaseous states. This transformation rarely on the latent head and the heralded molecular interactions as show in heating courses on the phase diagrams. and important terminal straits in the phase exchange in the interactor um, and the phase transitions often involved a broad volume change that generate internal straits, and while in the suit hating in the induces localist phase change and stroke parallel. Um, and summary understands the fundamentals allow of us to predict material behavior, prevent structural damage, design safer and the more efficient systems, and expense is countless process in the daily life. The relationship with Ben head straits in the phase transitions, he lived in the essential role of the psyches in the engineering, technology, and natural world.
One. Still this square hole in the center with a 5 same aim side when it 40, 40 a brass bar as a square cross section of 5 3 same aim temperature 14 and 1 the common temperature should they be should that the bar fits exactly in the hole in the disk 35 write the final length condition the bar must in the exactly in the hole the third final size must be equal ls 1a alpha s delta t lb 1 by omega b delta t. Mm, substitute the internal legs 1 by omega s delta t 5003 1 alpha b alpha t 3 expand both sides 5000 5000 alpha s alpha t 5003 5003 alpha 3 alpha b delta t. 4 groups terms with a delta t on one side, constants on the other. 5000 omega s al delta t 5003 b delta t 5003 5000 delta t 0003 5000 alpha 5003 5 factor of delta t 5000 alpha s 5003 omega b delta t 0003 5 solve for delta t 7 insert the coefficients still alpha 11 by 10 6 brass alpha 19 by 10 6 2 during the canning process of minor uh, 15 headspace must be considered allowed for the liquid suspension. The temperature change assumes that water is consumed at temperatures of 40 and the liquid is similar to water. The original volume of the aluminum canal 353 4 ml. The coefficients of volumetric expansion for water aluminum are 2, 1 by 10, 4 and 7, 2 by 10, 5. Respectively, water volume of water should be counted. Answer 352,785 ml. 1. Great expansion for the expanded volume of the aluminum can. B can final B01 A1 delta T. 2. Insert the values. B can final 354,172 by 10, 10, 5, 40, 15. Delta T. 4. Calculate the expanded can volume. Become final 354 172 by 10. 5. Write expansion for the expanding volume of the water. Be water final. Be fill 1 water delta T. 6. Insert expansion coefficient of water. Water final. File 1 to 1 by 10. 4. 7. Send the final volume square. Water must not excess the can. Be file 1, 2, 1 by 10. 4. Become final. 8. Solve for the fill volume. Solve for the volume. Become final 1, 2, 1 by 10. 4. Answer be file 352,785 ml.
Okay. Now, as we said before, this is an exercise that talks about the bridge joint expansions, and my partner or teammate Gabriel will read it and will explain it to you. I hope you understand.
A concrete bridge deck in 5 meters long, temperature of 50 degrees Celsius. During summer, the temperature reaches 45 degrees Celsius, and in when it drops to 10 degrees Celsius, the concrete is a linear thermal expansion coefficient of alpha 1, 2 by 10, 5 degrees Celsius 1. Questions. Calculate expansion of the bridge deck from weather to summer conditions. Calculate the contraction of the bridge deck from summer to winter conditions. The same considerations if expansion joints are placed every meters on the bridge. What is the maximum gap each joint must accommodate? Real world application. Why is it important to have properly sized expansion joints? Water problems could occur if the water too small. 1. Expansion from winter to summer. Use delta L alpha L 0 delta T. Delta 1, 2 by 10, 5. Hunger 5 by 55. 0, 3, 3. Meters 3, 3 mm.
2. Contraction from summit or winter, contraction magnitude is the same opposite descent. Delta L 033 meters. 3. Expansion joint signing where joints vary 50 meters. Interpretation merge segment expansion. If you divide the bridge into a segment of 50 meters, so each segment 50 meters long. The expansion of one 50 meter segment over the same delta t is delta L 50 alpha 50 by 55 0033 meters 33. So each 50 meter segment grows by 33 and if joints spaced on every 50 interface and each joint must accumulate the relative movement of one segment against a neighbor a gap and is required. Interpretation B where interfaces conservative if you count interfaces borrowing 10 segments there are 9 internal joins. Hunger 5 to 50 10 segments internal joints. The total expansion 3 3 must be taken by 9 joints, so each joint will need a dollar 330 9 367 9 330 3 6 6 7. So a conservative per joint gap 367. The gene recommendation of the large conservative volume and the margin in construction tolerance, creep openings, sealing material compression from head, possible future repeatings as safety factor, especially nominal joints capability of 40, 45 and per joint. Four, why properly sized expansion joints are important? Brief. If joints are too small, of missing thermal expansion will produce large compressive stress on restraint forces that can cause buckling or lateral deformation of the deck on rails, cracking and spalling of concrete, structural damage, failure, bearing, and more fatigue, fracture, distortion of the deck production bumps for raiding surface, accelerated wear, leaking to the main seal, leading corrosion, reinforcement, increased maintenance costs, and possible safety hazards. Properly sized joints allow structure to expand the contract without induced damage. Strengths include the main seals and a little extra gap of quick summary numbers. Total expansion when there's the summer 033 meters 330. Contract contraction summer to winter 033 meters. Expansion per 50 meter segment 33. Conservative gap for internal joints 9 joints 367. Recommended specifically 40 45. Nominal joint capacity allowed safety tolerance margin.
Well, well, everyone, that's everything. I hope you really enjoy it. I'm I'm forgiving myself
if I do not say this right. I hope you understand it. And good night. Yes.
Goodbye.
Thank you. Thank you.